last time than usual, just reviewing old stuff that I wasn't sure if you understood or not. I wanted to make sure you did. So that took up a little more time than usual. But let me put a couple more on the board here concerning PEMDAS. Like this simple one. Now remember, PEMDAS, order of operations, is to be used when you have an expression like this that you have to simplify. That's the instruction I would write if I made up your test. Other instructions could be calculate, or it could be evaluate. I've seen them all. But the point is there are no X's in it. Now, in about 15 minutes from now, we'll start having expressions with X's in it. That's what real algebra is about. But if you have an expression without X's in it, you must use those order of operations, PEMDAS. When you do have an expression with X in it, and you are told what X represents, in other words, X is some number, and you replace X with that number, then you're back to an expression like this without X, because you got just numbers in it. And then you would always use PEMDAS to evaluate it. That's why everything boils back down to this anyway. So what would you do first here?
Parentheses.
Good, you wouldn't add the 10 plus 2. That's what I really care about. You sure? Not even when you're under pressure. You're not going to do that. You're going to follow the rules of PEMDAS, which says do parentheses first. What if you really wanted to add the 10 plus 2 first? I mean, what if you're trying to get that across to somebody? I want you to add the 10 plus 2 first. How would you show that? That's what parentheses are for. So parentheses always say do me first. You put them, actually, I'll put it this way. If you believe somebody that you're trying to communicate with might misinterpret what you represent, even if you believe you're sticking to the rule of law and you know you're right, still, you don't want to take any chance of somebody misinterpreting what you write, correct? Especially if the odds are, if the situation is such that you can't afford a mistake with somebody's health or something like that, you want to make sure you communicate. Then I would always use parentheses around anything that you wanted to make sure that they do first. But in this case, yes, the 5 minus 3 needs to be first. How many operations are up here anyway?
3.
How many operations is in this?
3.
I think 3 is the right answer. One of them's plus, one of them's minus. What's the other one?
Multiplication.
Multiply, right here. The parentheses in and of themselves is not an operation. It's just saying what to do first, if there's any confusion about it. But we do see here that what we better do first is the subtraction. Then PEMDAS says do the multiplication, and then finally it says do the addition. It's just the reverse of the way it's listed. So 5 minus 3 is?
2.
2. Now please don't resist the temptation to add the 10 plus 2 at the beginning and feel so proud of yourself. And then do it here. You know? PEMDAS says multiply next. All right. Trying to think of another one on here I thought that was important. How about this? 9 plus 4 times 2 squared. Now each of these is bringing out mistakes that I've seen in the past. Now these are all taken from your work, from your homework. What's first here?
Exponent.
What does it apply to?
So the 2.
Just the 2?
Yes.
So you're not going to do this?
No.
Okay. Well, what if you wanted to do that first?
No.
You would do that. You would show it that way if that's what you really wanted to do, right? But it's not. So, tell me if I make a mistake. I've already used up my quota for today. Is that right?
Yes, sir.
Okay, that's the final answer. Maybe you understand it pretty good without me doing any more. Well, here's another one I've seen people through the years make a mistake. Now, this probably represents about as bad as you're going to get anyway on any assignment with PEMDAS. 2. Now, I hope when you're doing these problems that you put in equal and you rewrite the whole line. Don't just do a little piece of it, another one over here, another one in the back of the paper. You rewrite the whole line. That's what an equal sign means, but you make the one little change that PEMDAS says do. The nice thing about PEMDAS, it narrows it down to one thing to do. And I know us guys love to just have one thing that we know for sure we're supposed to do and not confused by a bunch of things. So you consult PEMDAS to what to do, and once you do it, you go back and consult PEMDAS again for the next line and the next line. What's the first thing here?
Parentheses.
The inner, yeah, not the brackets.
Inner parentheses, amen. 8 minus 4 is?
4.
Do I need the parentheses anymore?
Yes.
Really?
Uh,
See, I agree with you, sometimes yes. Sometimes yes, sometimes no. It never hurts to put them.
I was gonna say, just for continuity's sake.
It does, it depends on what the parentheses are there for. See, back up here, these parentheses were there for 2 purposes. You see that? They were there to say, do me first what's inside. But even when that's done, you still need the parentheses to show multiplication. So those parentheses were there for 2 reasons. Many times we can get rid of the parentheses once PEMDAS is done, but if they're there for another purpose like multiplication, no, we can't. Now here, once we get done with that subtraction, we don't really need them anymore, right? Because we can just write 4 squared that way. Now, if it had turned out to be negative 4, however, what if that had been 4 minus 8 instead of 8 minus 4 in the original problem? Then the result would have been negative 4, wouldn't it? 4 minus 8 is negative. Then you would have had to put the negative 4 in parentheses because the whole negative number is affected by the exponent. These just become second nature after a while, but at the beginning I can see you might have to think about it. But that's good enough for that line. Next step?
The exponent within the bracket.
Perfect. What is it?
16.
Oh, isn't that convenient? You guys are a lot of fun. 16 divided by 16?
One.
Word, one.
How about that? Now 2 times 1, right?
Yes. Negative 2 times.
Oh, negative 2 times 1. Is that right?
Yes, sir.
Well, I agree, but is that because you took 1 squared first?
Yes.
Yeah, I meant people, I'm just trying to catch people that would take the negative 2 times 1 first
No.
and then square it.
Exponent.
That's
comes
what
first.
you better not do, okay? But I agree it does turn into negative 2 times 1. So the answer is
Negative
negative 2. Every line got shorter. It's an upside down triangle. That's exactly what a perfect work on a PEMDAS problem looks like. Every line shorter. Good. You all feel confident with that? Don't get me in a picture, please. Well then, maybe we should go on to the next topic, which I had a public outcry for a few minutes ago before class. And that's, okay, if you're on my notes, I'm at the top of the 3rd page. We're still in 1.1, but when we finish this, we'll wrap up 1.1. My intention is to finish through 1.2 today, so we'll be on schedule. And I understand, since we didn't cover this the other day, you weren't sure of some of the answers when you were doing the homework. Now, what we're talking about here, this is down where it says, there are various general properties of quantities that need to be recognized. And if you count them, I think there are 9 there. There are 9 properties, many of which you've been using since the 1st grade, and didn't even realize they were a general property. It's just become second nature to you now. In fact, when you look at these, you might go, duh, I mean, everybody knows that. Well, the thing is, if it's always true, we need to write it as a principle or a property that we can rely on. Now, all of these 9 are. See, if you read down first the names of them, identity property of addition, identity property of multiplication, then inverse property of addition, then inverse property of multiplication, then commutative property of addition, and commutative property of multiplication, and associative property of addition, and associative property of multiplication. Now there you've got 8 already that just bounce back and forth between addition and multiplication. One thing we notice for sure, there's nothing there about subtraction, and there's nothing there about division. Nope. And then finally, the last one is the distributive property, which combines multiplication and addition, is what it does. So if we go back up to the top, on all of these 9, I've got written here a pattern, a form or a pattern. Now you'll be seeing these throughout the course. A pattern means that there is a principle here that this is trying to get across. You see, in a real problem, there's not going to be A there, there's not going to be B there, or C there. But you need to look at this and say, what is that really saying? Because if you can say it in words, in English words, what this is representing, then you really understand it. If you can explain it in words, even better than I can. So the first one, identity property of addition. Now it says A plus 0 equals A. I'm not going to write these on the board since you've all got them right here. A plus 0 equals A, or the other way around, 0 plus A equals A. What is that saying in words? And A represents anything. I think that's one reason we like to use the letter A in this case. It represents anything. By the way, letters at the beginning of the alphabet, like A, B, and C, typically don't represent variables. They represent constants, but unspecified constants, if you can follow that reasoning. Letters at the end of the alphabet, X, Y, and Z, are true variables. But if we have an expression with variables and constants, but we don't want to necessarily specify what constant it is, then we use letters A, B, and C. But in any particular problem, you'll know what they are. There are certain numbers or constants. Anyway, A plus 0 equals A. What is that saying in words? That if we take anything and add 0 to it, it doesn't change it. It's the same value. In other words, put another way, nothing loses its value by adding 0 to it. Say, well, I've known that since I was a little kid. But that is true. There's a name for that, the identity property of addition. See, these things are principles that we will use solving equations, all of these things. So there are names that are given to them so that you can recognize, okay, this is proper, this is legal to do, because it's one of these properties up here. All right, so you're going to have homework problems is the point, where they're going to give you an expression, and they're going to ask you, which of these properties does this represent? Is this an example of? So obviously, if they give you one where I don't care what A is, they could give you any expression and add 0 to it, and still say it's equal to the same original expression, you say right away that's the identity property of addition. Then the identity property of multiplication. A times 1 equals A. Interpretation. Multiplying anything by 1 does not change it. So you see why both of those are called the identity property. Adding 0 doesn't change it. Multiplying by 1 doesn't change it. Now, multiplying by 1 not changing something is very important, because sometimes we want to change the appearance of a fraction or any quantity. And as long as we multiply it by a number over itself, the same thing over itself, that's equivalent to 1. Anything over itself is 1. And all we're doing is changing the form of it. We're not changing the value of it. So effectively, we're multiplying by 1. And we can do that because the identity property of multiplication says we can do that. Stop me if you have a question. The inverse property of addition. A plus negative A equals 0. Or alternatively, negative a plus a equals 0. What does that really say?
Subtracting anything by itself will always give you 0.
That's pretty good. If you take any quantity and change its sign, and then add the two together, you're guaranteed to get 0. So anything added or combined with, let's use absolute value. Any number that is combined with a number that has the same absolute value but opposite sign will be 0. You see the value of algebraic notation. I mean, once you start understanding algebraic notation, it replaces the need for all these words trying to describe something to somebody. You know, at first, algebraic notation looks like something from another planet. But the more you work on it and use it, you become to appreciate it because it encapsulates a truth in a very small space. So, 6 plus negative 6 is 0, or 6 minus 6 is 0, or minus 6 plus 6 is 0. Anything plus its opposite. See, A and minus A are called additive inverses or opposites. Well, there's an inverse property of multiplication. A times 1 over A is 1. Now be careful not to put 0 there. A times 1 over A is 1. Put in words. Anything times its reciprocal. Right? Reciprocal means flip it over. So anything times its reciprocal is 1. Is it true, let me stop for a moment, that A could be positive or negative in any of these things? Is A restricted to be positive?
No.
No. In fact, I made a statement at the beginning there. All the symbols and the properties below can be positive or negative. So when we write a pattern, this will be true from now on, just because we use a plus sign doesn't mean it has to be positive. It can be negative. The value itself of the expression can be anything. That's what A means again, anything, positive or negative. Let's go back up to that inverse property of addition one more time. Anything plus its opposite or additive inverse is 0. I know what I wanted to say. Back at the beginning, identity property of addition. Let's go back to the first one. Anything plus 0 is itself. So if 0 is being added to anything, 0 indeed is meaningless, which is what we normally think of 0 to mean anyway. 0 adds nothing whatsoever if you're adding 0. But if you're multiplying by 0, which by the way is not on here, there's not one on here where you're multiplying by 0. But if you're multiplying by 0, what's true?
The value will always be 0.
0 wins big time. 0 wins over 10 billion. If you're multiplying. If you're adding 0 to 10 billion, 0 has no effect whatsoever. But if you're multiplying 10 billion by 0, the 10 billion has no effect whatsoever. So 0 goes all the way from being nothing to being king of the hill. Now, I used to love to give problems, especially like a extra credit problem on a test, where I'd have all these numbers being multiplied, crazy numbers, 15,346,000, 0.185, 10 to the minus 18th, all these numbers being multiplied, and right in the middle is this 0, just a little 0 right there in the middle, and all these other numbers stretching to the edge of the page, and some student who thinks he's got some extra time and get a little bit of extra credit will pick up his calculator and start doing all these calculations. And you finally get to the 0 in the middle and say, oh, I've been had. The answer is 0. Isn't that wonderful? Okay, let's go down to commutative property of addition. Now, these really are important from here on out. The ones before this you knew anyway, okay? And the truth is you know these too. But the commutative property of addition, A plus B equals B plus A. Now, the ones before this test had a single value A in it, didn't they? All they had A in it. Now, from now on, we have multiple values. So A plus B equals B plus A. What is that saying? If we're adding two numbers, what?
Reversing the order of the numbers doesn't change anything.
I like that, yes, sir. The order does not matter when you're adding numbers. Order does not matter. That's why your first grade teacher would say to you 2 plus 3 is 3 plus 2. She didn't say to you that, hey, this is called the commutative property of addition. She didn't even know that anyway. She just said, okay, so can they be negative? Yes, they can. You know, remember the other day when I was trying to get across to you to no longer regard a minus sign as being subtraction, but regard it as the sign of the number. The sign in front of the number goes with the number. I kept saying that the other day. Well, if you do that, then this negative numbers will apply to A plus B equals B plus A, because you can swap negative numbers around as long as you keep the sign with the number. If you insist on keeping the negative signs meaning subtraction, it does not apply to this commutative property of addition. That's the way the word addition is in the name. Commutative property of addition. But if you keep the negative sign with the number, then you can move it around. Yes, you can, and this will apply. Because you can swap numbers around of any kind and add them in any order you want, as long as you keep the sign with the number. Commutative property of multiplication. Ab equal Bob. Okay, so this is saying if you're multiplying two numbers, order does not matter. So 2 times 3 is the same as 3 times 2. You see why division is not in here anywhere, because none of this is true of division. It's true of adding, it's true of multiplying. Now, this helps because sometimes when we're solving equations, we want to swap things around. Sometimes when we're multiplying, we want to swap things around. For instance, if we have y times x, I never leave it like that. You change it to xy because you want stuff in alphabetical order. You want all terms to be in alphabetical order when it comes to variables. xy, not yx. So yes, this entitles you to do that. You can turn things around that are being multiplied if it's to your benefit to do that. Okay, associative property of addition. Now this is getting a little more complicated here. What is this saying? Where did I lay my mark? Lay it down somewhere. We'll use this one. A plus B plus C. Now B plus C are in parentheses equals A plus B in parentheses plus C. What is that saying? Well, first of all, we're talking about 3 numbers now, not just 2. The associative property of addition and multiplication has to involve 3. Makes no sense to just talk about 2. So what this is saying is that we're adding 3 numbers. But you can't do all 3 at once. You can only do 2 at a time. So the point is, right, if you're adding 3 numbers, it doesn't matter which 2 you start with. You add 2, take that result, and add it to the other one. Same way on a calculator, don't you punch in 2, and then punch in another one, and then punch in another one? And the point is, it doesn't matter which 2 you started out with. As long as you got your whole list that you're adding, eventually you'll end up with the same answer. So you see that that's what this is saying? You start out adding 2, but it doesn't matter which 2 that you start out with. And we can combine, actually, the associative property with the commutative property. The commutative property said the order of two doesn't matter. The associative property says which two you start out with doesn't matter. So when you combine those two together, it says if you've got three or more that you're adding, it doesn't matter which two you start out with, but whatever two you choose, the order of those two does not matter. Commutative property and associative property. They can be negative. And then the associative property of multiplication, saying something very similar. Now you understand, if there's no operation shown between quantities, it's understood to be multiplication, right? This is A times B times C. Really, those parentheses don't have to be there. And you know why the parentheses don't have to be there? For the very reason we've got this associative property, that the order does not matter. But this is implying that we start with B times C and then multiply by A. This is implying we start with A times B and then multiply by C. Therefore, the conclusion, when you're multiplying three or more quantities, the two that you start out with does not matter. And combining that with the commutative property, it's saying when you pick the two that you want to start out with, the order of those two also does not matter. Now that was 8 of them right there. Now the kind of problem I believe you're going to have on your homework on this is they're going to give you an example of some sort of property. They don't tell you which one. It won't be just like what I wrote on here. It'll be something else. Because A can be anything. That's what I keep trying to get across. So they're going to give you something else. But you have to look at it and recognize which of the properties are they talking about here. Are they adding 0? Are they multiplying by 1? Are they adding the inverse? Are they multiplying by the reciprocal? Are they swapping the order around? Are they grouping different ones to start out with? So you look and see what they're doing, and then you name the property that they're using. Okay. Did I put it in my pocket? No. Anyway, let's go back over here. The next one is the one that we'll be using all the time. The last one, the distributive property. Which generally for beginning students,
It's in your head.
no, this is an old one I don't like. It's like when I can't find my glasses and they're on my face. Okay, here's the distributive property. It was laying up here anyway. Now let's really understand what that's saying. The left side is saying, according to PEMDAS, we have two quantities B plus C that we're adding, and the parentheses are saying we need to do that first, correct? So this left side is saying add B plus C, get that result, and multiply it by A. So two operations. Add B and C, and then multiply the result by A. Now what's this saying on the right? PEMDAS says do multiplication first, right? There's no parentheses over here. So it's saying take this A, which out here is on the outside, and multiply by the B. Also take the A and multiply by the C. Two multiplications there. And take those two results and add them. And this is saying you will guarantee to get the same answer when you do that. Now really on the left there's only two operations, one addition and one multiplication. Over here there are three operations, two multiplication, one addition. But they're the same. We usually show this by drawing these curves, and I do this all the time. When you draw these curves, it's saying this A out here on the outside is multiplied times B, and it's multiplied times C. This plus can be a minus. Well, they all can be negative. They all can be negative, but the sign in here could be minus, in which case it's AB minus AC. Still being distributed. Now the question is, when would we ever want to use that? Answer to that question, if there are only numbers in the original expression, no x's, there's no reason to ever use this. Because PEMDAS would say, if there are only numbers, just do here. Add the numbers in the parentheses, that's what PEMDAS says, parentheses first. Add these numbers, multiply by the result. There's no reason to do this. Now let's take an example. If this is what we have to calculate, you know PEMDAS says, that's it, isn't it? That's what PEMDAS would say do. Now the distributive rule property says, wait, I can distribute this 2. Take 2 times the 3, plus, keep whatever signs in the middle, see, plus 2 times the 4. And if I do that, I should get the same answer. That's what distributive property is saying. So we get 6 plus 8. I'm just verifying for you that the distributive property is correct. You can do it this way, or you could do it this way and get the same answer. But once again, if it's only numbers, no x's, you might as well just do it this way. That's the way we were doing it. Might as well continue to do it. This is just an alternative way. Now you can check your work. This is nice. If it's 2 ways to do something and you got time, you might as well do it the second way and see if you get the same answer. It's a check. So you can go ahead and do this and make sure you get the same answer. Of course, the steps are different, right? Every calculation was totally different, but you ended up with the same number. The bottom line, though, is there's no reason to use the distributive property until we get to x's. Then you're going to have to use it. But when it's just numbers, you might as well just continue to use and do what PEMDAS says do. All right, I said all that in one sentence there at the end, didn't I? The distributive property is most useful when variables are present. As we will see, it is generally unnecessary to use it when there are only numbers, since PEMDAS is the accepted procedure. End of 1.1. 1.2, evaluate and simplify algebraic expressions. So we're starting real algebra now in 1.2. As soon as we get x's in it, that's when some people start getting scared. You first of all have to define what an expression is, or an algebraic expression, but we just always say expression. An expression has numbers in it, which those numbers can be any of the numbers on the real number line like we have on the board on Tuesday. Rational, irrational, but we never use anything but rational in these expressions. So it has numbers in it, it has operations in it, and we put a list of operations on the board last time that we know now. Add, subtract, multiply, divide, square, square root, and absolute value. Those are the ones we know. And finally, variables. Most common variable is x. X, y, z, any of those letters like that. So the natural question at this point is, why do we have variables? We haven't used them up to now, and I've been perfectly happy. And what are these variables for? Like x, for example. Well, there are 2 uses for variables. So I'd like for you to understand that. One use for a variable is that it's just sitting there, and generally as part of some other expression, with numbers, operations, it's in an expression. And it's just sitting there waiting for somebody to tell you what X represents today. Because X represents some number. That's what it's for. It's just sitting there as a name. You're just waiting for somebody to tell you what it really is, so that you can replace X with that number in the expression. And once you replace X with the number in the expression, it's all numbers now, and you use PEMDAS to calculate it. You can't use PEMDAS till somebody tells you what X is. So an expression that we're going to be using some examples here, just sits on the shelf waiting for somebody to tell you what X is. That's what it's meant for, is to be evaluated, calculated, once somebody gives you a value for X. You can have multiple variables in it. It could be X, Y, Z. What that is similar to formulas. You know, you have formulas for all kinds of things in every branch of science and medicine, all these formulas, same kind of thing. Those formulas just sit there waiting for somebody to tell you what the values are, or you have to go out and do some measurements, calculations, or something, right, to come up with those values. Then you put them in there and calculate. You've got to be so careful. Oh, I was helping a student with physics this morning, because some students here have to take physics, namely in cardiovascular sonography. And it starts right off with a bang. I mean, talking about trig and stuff that we don't even get into in here, but it points out you've got to be so careful about units of measurement. When you're calculating something, you've got to first know what the formula is requiring. Is it inches? Is it feet? Is it meters? Is it degrees? Is it there can be it could be feet, inches, anything. Could be measurements of anything have different units. Europe has got different units than we got, So you've got to make sure you have the right formula. You got to make sure that what units the formula requires in it, and you got to make sure you're measuring it in those units, or you know how to convert to the units that it wants. Because it's so easy to put the wrong stuff and get out a totally wrong solution, and you go on and use that. For this particular patient or this job, this happens a lot in the past, right? You've read some stories about it, only because somebody wasn't careful on getting the right value for X and plugging it in and calculating it correctly. You get your calculator out, you got to make sure you get stuff plugged in correctly and calculated. A lot of room for error on these things. Well, getting back to what I said, that's one use of X, waiting for somebody to tell you, or you come up with what the value of it is by some other independent measurements. Now, this is for an expression. When we get to Module 2 next time in 2.1, we won't be working with expressions. We'll be working with equations. Now, there's two main things we talk about in algebra, expressions and equations. They both have X's in them, but X is treated differently in them. Again, in an expression, X can be anything. You're just waiting to figure out what it is in this particular case. And once you know what it is in this case, you put it in there and calculate. But when it comes to an equation, which has an equal sign in it, that's the difference, right? When it comes to an equation, X can only be one number. And you're not waiting for somebody to tell you what that number is. You have to come up with it. You have to be a good detective and figure out what that one single value of X is that will make that equation true. So X has two uses. It can be anything in an expression. It can only be one thing in an equation. In an expression, somebody tells you what the value is. In an equation, you have to decide what the value is using the procedures we will talk about in 2.1. Wow, that was a sermon and a half. So, an expression has numbers, operations, and variables. And we've talked now about what a variable is, so the next thing is, what's next on there? To evaluate. Okay. When we have algebraic expressions, there are two most common instructions for them. Read the instruction carefully. One is evaluate. The other is simplify. Throughout this course, we'll be using both. We'll actually be using simplify more than evaluate. Every time we talk about a new kind of expression, every chapter's got a new kind of expression. New kind of expression, it's different. But every time there's a new expression, there's a new way to simplify it. So you'll see the word simplify all the way to the end of the course. And on the final exam, there'll be all kinds of problems on there, and the only instruction is simplify. And you have to look at the problem and see what kind of expression is this. Is it a polynomial, which we'll get to today? Is it a rational expression, which we get to in Module 6? Is it a radical expression that we get to in Module 7, for instance? And depending upon what kind of expression it is, you have to remember what you need to do to simplify it. But we'll get to that in a minute. We need to talk first about evaluate. So what does evaluate mean? Evaluate means, we're talking about an expression now, not an equation. So evaluate means replace x with a given value. Okay? And then calculate by PEMDAS. That's a simple concept. You have this expression with x, you're waiting for somebody to tell you what x is, put it in there and calculate it. Let me use these same two examples I've got on the handout right now, and then I've got a couple more, I guess. 3x cubed minus x squared plus 2x plus 9. Now, the work's all there on the paper. But this is very typical of the kind of expression we'll be using a lot in this course. This is called a polynomial. These are terms, right? 4 terms there in a polynomial. We'll be discussing that more later in 1.2. But that is an expression. It certainly has numbers in it. It certainly has operations in it. It certainly has variable in it, and then you one variable x. And the instruction will be, in this case, read the instruction. Don't do anything without reading the instruction. The instruction is evaluate for, what does that say on here? X equal? -2. Well, there are 2 steps. Replace and calculate. And if I was grading your problems on paper, I would expect you first, in the very first line, to put the whole expression with just x replaced with -2. Don't do any work, just replace x with -2. That proves to me that you know what evaluate means. The first step is to replace it. And you better replace it everywhere x appears. Don't overlook it. And if it is a negative quantity you're putting in for x, always put it in parentheses. Now, sometimes a positive needs to be in parentheses too, to make it clear what you're doing. But every time it's negative, it has to be in parentheses. So, you've got to do this. Now, why do we have to put in parentheses, but we didn't have to put the x in parentheses? That seems unfair. Because if we don't put parentheses here, it looks like subtraction. Right? There's no ambiguity here with the x. That's x 3 times cubed and then multiplied by 3. But if you're going to replace x with the whole -2, you got to show, remember we went through this last time, that the whole -2 is affected by the exponent 3. So you got to put the parentheses there. Or otherwise it'll just look like only the 2. The whole -2 is being cubed. Okay, now, this minus. The biggest mistake people make on this is signs. This minus copy it. Now, this x again is being replaced with -2. So you gotta put parentheses, -2 squared. Plus 2, there's x again, parentheses, -2. Finally, plus 9. Now you see why you shouldn't be doing too much in your head. Please write that down first. Then you've got to copy this, calculate this correctly. Sign is the big thing. Now, of course, PEMDAS says, because we only got numbers now, so we're using PEMDAS, okay? Now, PEMDAS says, do the exponent first. And there are 2 of them. And we can do them simultaneously. They're not inside each other. They're separate. So I think if we're going to follow PEMDAS explicitly, let's do this -2 cubed. So this 3 is waiting its turn. -2 cubed.
-8.
It is -8. Now, does anybody have trouble seeing that? I mean, if you're not sure, write it 3 times. That's what it's meant for. Cubed 3 times. You know, you can write it 3 times. And I taught you last time, get the sign first. For all that. Get the sign first. Well, there are 3 negatives, odd number of negatives. I know the answer is going to be negative. And then you can multiply these in any order you want. Truth is, you can take 3 times 2 first if you want. You know, if you write all this out, everything's being multiplied. And we just had the associative law.